All right, Dev, can I start now?
Yes, Macarius.
Okay, great. Well, welcome all of you. Good afternoon. Today, we continue with the Translational Data Analytics Institute speaker series. And I have the most distinguished honor today to introduce our speaker, Dr. Elizabeth Chen. She's going to talk about artificial intelligence in healthcare, the challenges, the opportunities, and the highlights. I believe most of you have seen her abstract, but just a one-liner. I am very excited about what Dr. Chen is going to talk about, and especially the use of this publication on AI in healthcare, the hope, the hype, the promise, and the peril, as an illustration or demonstration of how AI techniques work in different clinical contexts. For me personally, my research has a lot of overlap with what Dr. Chen is going to talk about. So this talk is of great importance to me and relevance, and I believe that most of you feel the same. Dr. Chen is currently the interim director of the Brown Center for Biomedical Informatics, and she's an associate professor of medical science, as well as in health services policy and practice at Brown University. Dr. Chen is the director of the Advanced CTR Biomedical Informatics and Cyber Infrastructure Enhancement Core, and a faculty scholar in the Hestenfeld Child Health Innovation Institute. Dr. Chen leads the Clinical Informatics Innovation and Implementation Lab that is focused on leveraging electronic health records technology and data to improve healthcare delivery and biomedical discovery. Dr. Chen's current research projects involve the use of data, technology, and computational approaches for improving mental health and child health. Now, Dr. Chen's portfolio, as you can see, is heavy, and I have no idea how she's able to wear different hats and still be as accomplished as she is. Dr. Chen is currently chair of the Biomedical Informatics Library and Data Sciences Review Committee for the National Library of Medicine and the National Institutes of Health. She is also an associate editor for Methods of Information in Medicine and on the editorial board member for the Journal of Biomedical Informatics. Now, I can go on and on about Dr. Chen's accomplishment because the list is endless, but I would like to stop here and give Dr. Chen the opportunity to give us this wonderful talk that we are all anxiously waiting to hear. Dr. Chen.
Great, thank you so much. Hopefully you can see the slides okay?
Yes.
Look okay? Great, okay. Thank you so much for that wonderful introduction. It's a real pleasure to be here. I look forward to talking with you and about artificial intelligence in healthcare, challenges, opportunities, and highlights. So the plan for today is really, again, to first talk about some of the challenges and opportunities, particularly in that National Academy of Medicine report that was mentioned, and then highlight some of the projects that we're actually doing in Rhode Island to kind of demonstrate how we've been using different AI techniques in different clinical contexts. Before I kind of jump into things, though, it might be helpful to kind of look at our history of AI really as a field starting back into the 1950s, lots of excitement. If those of you remember, maybe some of your early programs were in kind of games, tic-tac-toe, checkers, and teaching the computer to play games. Kind of going on, fast forward a few decades, really growing interest in machine learning beginning to flourish, things like trying to classify things. And now more recently, a lot of interest in deep learning. And so really kind of seeing there's so much has evolved with artificial intelligence. And on the right, kind of just showing that, within AI, machine learning, a subset of that, deep learning, a subset of machine learning, and also natural language processing, also kind of part of artificial intelligence. And we'll talk about, all of these techniques throughout this talk, mostly at a high level, and just kind of showing how it can be used. And many of you may be using these already, but thought it might be useful really kind of focusing in the healthcare context. So here's kind of another view, a little more detailed about kind of the history of AI in medicine and really going in parallel. And so, development in the medical field, also kind of starting around the same time in the 1950s. This one to highlight here, one of the first systems of AI in medicine, MYCIN. And so oftentimes this one is cited in AI textbooks, really focus on, this was a rule-based system, focus on infections and identifying treatments for infections. And many of the systems after that, things like eMycin, were really based on that initial work in the early 1970s. I think this is a really nice kind of visual of showing we have experienced what they've called AI winters, where there's lots of excitement, lots of hype about the potential of AI, but for a variety of reasons, not really living up to that hype and kind of going into this phase where there's a lot of excitement, it kind of stops for a while and it picks up again. And so we've experienced that in the 1970s and to 1980. We've seen kind of more development in AI in medicine, another AI winter in the 80s and 90s, and then kind of seeing the emergence of deep learning. And now we're kind of seeing, again, a lot of excitement. And again, the hope is that we don't enter another AI winter, but a lot has advanced, technology has advanced. We have new fields that didn't exist before. And so there's a lot of interest in this area. And so a lot of development kind of out there in the real world, as also within healthcare. And so this was a visual from focus on gastroenterology. So talking about some of the things that they've been doing, but really we're seeing it everywhere in healthcare.
Hey, Liz.
Yep.
I apologize for interrupting you. Can you put us into slideshow view? That looks better.
Nice, that happened. Oh, sorry about that, everyone.
A little easier to see. Thank you so much.
Okay, so now getting to some of these challenges and opportunities. As I mentioned, seeing AI everywhere. And so everywhere you go, everything, your daily activities, there's probably AI in everything that we do at this point. But focusing on applications in healthcare, we're seeing the use of AI for a diagnosis, use for imaging, finding anomalies in medical images, drug development, within our electronic health records, we're seeing the use of, alerts, best practice advisories, talking about to do some prediction, of readmissions or particular diagnoses. Lots of use of AI in medical research. We're seeing it in our wearables and just a variety of other areas, and also different clinical specialties, mental health, also different settings, either the emergency room or surgery. So really, again, it's everywhere. But the question is, how do we actually put it into practice and make sure it's working as we had hoped? So this report is a really, it's a good read if you haven't seen it yet. So it's part of the National Academy of Medicine, the Learning Health System series. And so there's actually a whole range of books. I think the first one came out maybe 10 or 20 years ago about what the learning health system is and really wanting to take data to learn from it and then put what we learn into practice and be able to study whether or not there's change. And so there was one, and then it talked about all the different pieces that go into a learning health system, the data infrastructure that needs to be there. And then this is one of the more recent ones that came out last year, a focus on artificial intelligence in healthcare, the hope, the hype, the promise, the peril. I think it's still available online. I don't think there's a book version yet, but still, it's actually kind of summarizes all the different pieces, all the things that we've been working on for decades and kind of putting it together and, how do we actually put this into practice? And here is just a visual of the chapters in it, kind of giving the overview and really kind of balancing, there is the promise and the hope, but also the peril and the hype, and really trying to balance both sides of that. They talk about use cases, model development, and then also thinking about implementation. We'll probably focus more on kind of the model development, kind of being able to analyze data, but also important to talk about, how do we actually put it into practice? And then of course, legislation and regulation, all relevant to this. So again, if this is an area you're interested in, if you haven't seen this, it's, whether or not you just flip through it or read it, there's a lot of great information in there. It really talks about also the history, a lot of the things that have been developed over the years, how we all bring it together to enable an AI-enabled healthcare system. But just wanted note a couple of things that they talk about throughout this report that really, as you're kind of engaging in these studies, to think about making sure your data is representative of the population. There's a lot of concerns these days with, having bias, making sure it's representative. So that's something that they talk about is, that we need to have accessibility, standardization, and quality. We really need to prioritize ethical, equitable, and inclusive healthcare while addressing bias. Things that come out now is a lot of people say, well, it's black box. And so really thinking about how can we encourage transparency and trust, because these are critical things. This is our healthcare. So making sure we can actually trust what the computer might be telling us and also understanding what we're being told. This one I think is also important. We talk a lot about this when we think about clinical decision support, and we're always careful about saying clinical decision support. So these tools are here to help you support, not make decisions. And this is also something that's noted is, as of now, and probably I would think, forever, is really an augmented intelligence. So we want to enhance the clinician or enhance patients as they're making healthcare decisions and not necessarily make these autonomous AI agents. And so really it's the computer and the humans working together to make decisions. As you can imagine, we need more people trained in this space. And so training and educational programs, we have a lot of programs out there that have been established in informatics and data science. And then a lot of them already do training in healthcare AI, but we definitely need more if this is something that needs to be advanced and that we need to invest in. We talk about this a lot, we need to have these frameworks and best practices, and we don't have to keep reinventing the wheel. So there's been a lot of efforts to think about best practices, standards, frameworks for things like the learning healthcare system. So if we develop it, and there have been a lot of great success stories across the country that we can learn from and not necessarily create from scratch. Things that are also important as we think about systems, human factors, implementation science really growing as a field to address challenge and when we actually think about operationalizing or putting AI into practice. And then also really balancing innovation with safety and regulation legislation to promote trust. So we can't just build these systems. We really need to think about all these other things related to regulation and legislation out there. So that's an overview of things. And I thought I'd kind of maybe go a little deeper and kind of particularly from the data parts of kind of the AI life cycle is kind of what are things that you need to do. And so these two graphics show kind of the steps in trying to transform data to knowledge. The one on the left came out in the 1990s, and it's often ones that when I was doing graduate training is the one I looked at is, I have this great data. So I have data from my electronic health record. How do I turn that into knowledge? What are all the steps? And so this was a nice visual of just saying, well, there's a lot of steps that go from there. We need to select the data, and a lot goes into trying to figure out who should be included in your data set. For those of you who do a lot of work in this, I think probably everyone on this call is pre-processing. You spend lots of time cleaning your data and dealing with a lot of dirty data issues. And then you transform it, depending on what technique you're using, whatever data mining or machine learning technique you might be using, you might need your data in a particular format. And then finally, you get to a place where, okay, you've learned something, you have these models, but now you need to interpret them. You might need to work with clinicians, researchers, patients to really understand what are these models telling us? Is it working well? So evaluating it. And then we have kind of our knowledge. And then the next phase after that is how do we turn this knowledge into practice, whether or not it's, some kind of resource or a clinical decision support tool. But again, there's lots to do in this phase. And what we often will say is the selection, pre-processing, transformation is typically 80 to 90% of the work. Hardest part is getting your data, cleaning your data, getting in the right format. And in theory, the steps afterward can be pretty straightforward. But of course, oftentimes you'll need to configure things, test different parameters and things like that. But oftentimes the hardest part is just getting the data that you need in the right format. On the right is with data science, there's some newer frameworks that have come out, but if you look at them, they're very similar to the KDD. They may be newer words, but this one kind of shows the same thing as we have a lot of great new tools out there, new programming languages that didn't exist, in the 90s. But the same kind of thing, we need to collect our data. We then may want to explore it. You know, what are my fields? What's in this data set? What are some of the issues, data quality issues I might encounter? You will want to clean it, munge it. So again, this new terminology, munging versus pre-processing, transforming, but essentially trying to get to the same thing. We then need to model, create models from our data, validate it or evaluate it, and then finally report it. And there's lots of great tools to do that for visualization, things like that. But again, just to kind of show the different steps in the process. And there are some who focus on, you know, one of these, some that try to do them all, but all really critical to actually figure out how to get things from data to knowledge. Here, what we did a few years ago was to take basically that knowledge discovery and databases framework and say, let's apply it in the health context. So what are the things, like when we're working with health data, like electronic health record data, what are the things that we typically need to do? And so kind of take a more generic framework and put it in the health context. So in the left, kind of show some of the data sources we might work with. So EHRs, electronic health record, those data typically stored in a real-time CDR or clinical data repository. Those data may then get put into an enterprise data warehouse, and these may have varying names, different institutions that have data from our EHR as well as other systems that might be available in your institution's registries, biobanks, maybe claims data, literature, and just really all coming together here. And then the first question might be like, you know, who's your population? What do you want to study? And so there's a lot of work out there in cohort identification or EHR phenotyping algorithms of how do you identify patients. So if I'm thinking about, you know, I'm interested in studying asthma. Okay, what are my ICD codes? You know, do I want to study children? Do I want to study adults? Are there certain criteria, inclusion, exclusion criteria, and really going through that exercise of figuring out who should be in your cohort and then who should be the cases, who should be the controls. And so that can be a pretty significant step. And then figure out, okay, for those patients, what data do I want to extract? And so this tries to show, well, we might have structured data, so things like diagnoses, problems, and medications, but we also might have unstructured data, clinical notes and clinical reports that we need to turn into structured data using natural language processing. And so these try to show some of the steps, and then you may need to transform your data. So if you're using data from structured parts of the EHR or unstructured, we turn them structured, then we need to integrate them together and then go through the process of using our data mining or machine learning techniques, learning from it and interpreting it. And then here kind of shows some of the steps you may need to address. And then here, really fundamental to all of this is standards. So that's oftentimes, I think, every talk I have to talk about. Again, more of the things that are behind the scenes, but standards and interoperability really being important throughout this process. And also thinking about if you want to collaborate, if you want to share, everything needs to be standardized in some way. And again, also emphasizing the importance of privacy and security. And so oftentimes needing to de-identify your data, use it in a secure environment. All these things need to be thought about as we kind of engage in studies involving health data, including electronic health data, and kind of in an AI context. So kind of what I thought I'd do is kind of step through some of these steps. But if we kind of start with data, we hear all about big data. There's so much data out there. And some of the issues is there's lots of data. It's coming at us very quickly. There's lots of variety of data. And so we already talked a little bit about there's structured data, there's unstructured data. But then if you think about all the data sources, there's so many different kinds of data. Things that we get concerned about too, you know, we often talk about things like junk in, junk out is we need to have good data so we have good models. If the data aren't good, the models won't be good or accurate. And so really looking at data quality is a big concern. We want to show the value of data. So if you get so much data, how do you actually get the value, and really highlighting how those data are useful. Validity, those are things kind of getting back to data quality, making sure our data accurate. We often will deal with issues with missing data, conflicting data, you know, how do we address those things? Variability, you know, your dynamic data, so data can change. And so what does that mean within a data set? Vocabulary, I think I emphasized this is really important, having these standard data models, semantic, syntactic, interoperability. And then vagueness, we oftentimes run into this, is just like, you have this data, but what does it mean? And so really just, I think, highlight, you know, when we talked about big data, it started as 3 Vs, then there were 5 Vs. I think here shows 10 Vs, and I think there are even more Vs. But again, just, you know, there's just lots of complexity with working with data that need to be considered. Looking at this in a health context, I think I mentioned this a little bit already, but there's just many sources of big data in healthcare. So as mentioned as part of the introduction, I spend most of my time with electronic health records and sometimes trying to integrate them with some of these others. Others in the field may focus on these different ones. So there are those particularly interesting kind of wearables, there's social media really focused on learning from those kinds of data, patient portals, so where patients can enter their data, lots of work in collecting data for different research studies, clinical trials, payers, claims databases, generic database, genomic data, just lots of different data. And then this one on the right, which I think this is actually a really good paper if you haven't seen it. It's pretty short, but just I think this visual is pretty effective in just showing there's so many different types of data out there, ranging from medications to diagnoses to family history to environmental data. A lot of it is structured, some of it's even coded. And so these are some of the commonly coded data you'll see. So ICD for diagnoses, CPT for procedures, Loing for labs and observations. But there's lots of these other data that you might get outside of a healthcare setting that's structured. And then here on the right, I think the things that we've seen is that a lot of data, significant amount of our data are in unstructured data, so free text. I think some of the reports are up to 80 to 90% of data. And so if you really want to have comprehensive data, is needing to combine structured with unstructured. And so again, in the clinical context, we'll see free text and things like chief complaints when a patient might come to me. They have clinical notes, reports, and then kind of social media data. There's lots of information that's being collected that you may not see in EHR data. And so lots of work in this space of trying to turn this textual data into structured data. And so we'll probably, the stories I'll be kind of telling will really focus more on EHR data, but just really to kind of show the landscape of data that are out there. Data standardization, I kind of mentioned this a little bit, so you'll hear a lot about, things like data models and common data models. And so one of the things that they talk about in this National Academy of Medicine report for AI is this is the recommended data standardization framework to promote AI system development from high quality, transparent, and interoperable data. So this is kind of when we need quality data because that will produce quality results. We need to understand where the data are coming from, and they need to be interoperable. So if I wanted to do a study in my institution, share it with your institution, we basically speak the same language because we have essentially interoperable data. So I thought this was a pretty nice graphic that shows here are different data sources. Here's the EHR, here's patient-generated data, administrative data, other clinical data, and really just other data, and all the shapes representing that they essentially are different. So right now, they all may be using different representations, different codes, even basic things like dates may be in different formats. And so you can't really bring them together. And so if you really want to be able to do that, they need to be speaking the same language, essentially have a common data model. And there are a whole range of common data models out there. The one you may hear more about is one called OMOP. So the Observational Medical Outcomes Partnership model. And so we've been working on mapping a lot of our data into that model to, again, make it interoperable to support AI studies. But here you can see now the shapes are all the same shape. Even though they're different colors because they're represent different data sources, but now essentially they speak the same language. So now you can combine them. And so here it says we combine them into a flat file. And then as we know, when we do studies, sometimes there's one file, sometimes there are multiple, sometimes it's in the database. But essentially now, because they speak the language, we can combine them together. And now because they're in the same format, we can apply our AI algorithms. And so I think this kind of really shows, of course, there's a lot of complexity to actually do this. But this is really our ideal state. If we really want to do effective and rapid AI system development, this is really a critical step, is getting our data in this standardized format. On the right, this is an example of natural language processing. And so oftentimes our data, as I mentioned, are in clinical text. And so we don't want to pull every single piece of information, but there may be critical pieces of information in our text. And so here, this graphic tries to show we have information about diagnoses, family history, symptoms, and other information in this note. And ideally, we would have algorithms and tools, natural language processing algorithms and tools to pull out this information. And then ideally, not just pull it out, but map it to some kind of standard. And so one of the resources that we can use is the Unified Medical Language System, which has all these different terminologies or coding systems inside of it that can be used for different purposes. So ICD typically for diagnoses, SNOMED for kind of information broadly in electronic health record, ARCS norm for medications, LOINC for observations and lab results. And so what we could do is use NLP systems. They'll pull out that information, and a lot of them will also then map to what we call a UMLS CUI, or concept unique identifier, and then essentially is standardized. So there are, again, a range of tools that have already been developed over the years. They're full systems, and I'll talk a little bit about some of the ones we've been using. There's specialized algorithms, so there's systems that can do all of this, pull all this information, map it to a coding standard, so then we can then integrate it with structured data. And then there's specialized systems for certain things. So some of the work that we've done early on is really focused on family history and social history, and developing standalone modules to do that. We're seeing a lot more tools that are doing that now, as well as full-blown systems that have that integrated in. But oftentimes, if you're working in a very specialized area, there may not yet be an NLP tool or algorithm available that works. You can start with one and then see how it does, and then you may need to make adjustments. But that's also these just to kind of highlight some of the core things that need to be done just to kind of get your data ready for analyses. Machine learning models, lots of different models out there. So this is a visual that you may have seen, but just, the different kinds of machine learning techniques. We have our, unsupervised learning. So things like clustering, where we may get a data set and want to study, different groupings. And so kind of going back to the asthma example, say, okay, I have this great data set for asthma patients, but I want to see, are there certain groupings that naturally kind of fall together? And so I might apply clustering techniques to see if there's some subgroups, and then try to understand why they're grouping in a certain way. And then on the right-hand side, supervised learning. So things like classification. Can we, anticipate that someone may be at risk for getting diagnosed with asthma just because of certain information that we've seen in their EHRs over time? Or is someone at risk for developing some kind of complication from surgery, or maybe at risk for readmission due to a variety of information that might be available in their data, so in their electronic health record. This visual on the right, I think also kind of shows the axes of machine learning and big data, and kind of in what I think is important to kind of look at here is the human to machine decision-making effort. So here shows where it's really just the computer. There's not a lot of human intervention. Starting from here is mostly the human. So things here like clinical knowledge, clinical wisdom, that's really kind of the human or the clinician, working with the patient and kind of using their knowledge to come up with some decisions, whether or not it's diagnosis, management, or treatment. Here, this kind of shows, okay, there's a little bit of computers here. So some of the expert AI systems, the one I mentioned, the Mycin system, a rule-based system. Here, supporting the clinician, but it's really the clinician, ultimately making the decision with some input from this AI system. As we've seen over the years, deep learning development. So that's what all of these are. We see there's a lot more of the computer and some human, and then also the data, needing more data and these different techniques. And then all the way up to here. And so this kind of gets to the challenge where we talked a little bit about is the black box. And so as we kind of go through these methods here, a lot of these early systems were essentially if-then rules. So if you see this, then do this. And so it's very clear, transparent, explainable. And as we've kind of gone to these newer tools and methods, we've entered the black box problems. Is we have input, we have output, but we don't know why a decision was made. And so that's where we're starting to see work in explainable and transparent AI. And I think, again, this visual kind of shows it well, is that we're entering this new age of AI applications, machine learning be a core of that. But what we are seeing is that these models are opaque, non-intuitive, difficult to understand. And we're seeing a lot of applications, not just within medicine and healthcare, but really just in any industry. And so we have kind of the user that's saying, why is the computer doing this? Why isn't it doing something else? When do you succeed? When do you fail? Can I trust you? And then how do I correct that error? And so this is really kind of a lot of what we're seeing now is this is where a lot of our work needs to be in, is explaining and being transparent. And so again, going back to this National Academy of Medicine report, they had this nice figure that I think summarized it well, is what are the different forms of transparency? So transparency can mean a lot of different things. And so in here it says explainability. So how does the algorithm reach its results? And that kind of gets back to our like machine learning models and algorithms, is how is it working? How did it get from input to output? Another part of this is the data set. We talked a little bit about that. It's like, where did it come from? So we can get this great data set, but oftentimes the challenge is we don't know how the data were entered. And so really understanding clinical workflows, understanding ideally how the data were entered by the clinician or patient or whoever the source may be. And then how were they processed? So when we get a data set where it's a lot of things changed, that we don't know about. And so really having insights to that, because that can really have impact on our downstream analyses. Similarly to algorithm, how is algorithm developed and validated? There's lots of great algorithms and models out there, but really understanding what they do. And then oftentimes, I think as we may see that AI systems really have many different pieces. And so how do they work together? So we oftentimes talk about things like pipelines of going. So as I showed earlier, data to knowledge, there are many different steps there, and knowing how all of those work together. And so it's not just an individual step or module, it's really the many different methods coming together and then really working together. Kind of getting to the next step. So things to think about as you're engaging in development of AI models, and then kind of the next step of putting into practice and application development. Here are some of the key considerations that they talk in this report. So, before you start these studies, what's the downstream intervention going to be? And so what's shown in this table on the right are things like, are you working to try to improve diagnosis, looking to improve prediction or prognosis, or is it treatment? And who's your target? Are you trying to help payers, patients and caregivers, or providers? And so, if we kind of focus on this one talks a little bit about, if we're focusing on really helping patients, can we help estimate risk of having an undiagnosed genetic condition? And what would this look like? And so if we can imagine, a patient seeing their provider, they have this electronic health record system, and it would be great. And there are already success stories for doing that somehow this system, there's some model that was developed and that it was put into the system and is able to tell them at the point of care, oh, based on all this information about this patient may be at risk for having this condition. And so that's an example. And so maybe it's some kind of clinical decision support that you might see within an EHR. And that's really where we're seeing a lot of effort being put in now, that we've done model development. Institutions are at various levels of progress in there, but now think about how do we actually put it into practice, whether or not it's within our EHR or some other app. We hear a lot these days about things like Smart on Fire apps, things that you can actually build upon that are essentially EHR agnostic, and being able to build that and to have it work with different EHR systems, but they're not embedded in the EHR. They're kind of a standalone, but can talk with the EHR using standards like Smart on Fire. So that's just one example, but these are the things to think about, when you start these studies, is what's the intervention going to be? Is it a computational intervention? It doesn't need to be, but is it something that I might want to add into an existing EHR system? Who's the target user? And so that's what it gets to is, is it the patient? Is it the provider? Is it someone else? What are the mechanics of executing the intervention? This oftentimes gets more into kind of maybe system development and software engineering, is how do you actually put it into practice from a kind of a development perspective? What happens if it fails? What if there are adverse events? These are all the things that we have to think about. We can't just put it in there and say, go. We have to think about what happens if it makes some wrong decisions. Was the capacity to intervene given existing resources? So can we kind of intervene with these tools? What's the accuracy needed? And these are the things. Is it, in some cases we want to, favor sensitivity versus specificity. We know it may not be perfect, but in some situations, we're really, having a false positive or negative can have serious consequences. So things like that need to be considered. And what's the desired outcome change following intervention? So, obviously, the ultimate goal is to improve healthcare, but what are some things that are tangible and feasible? So kind of knowing if we're able to study risk of a condition earlier on, can we start then giving treatment and kind of try to address it earlier on? And so, that's an example of a particular desired outcome. Some of those tools are focused on readmission. So, a tangible outcome there is, can we reduce readmissions because we've now learned, we've developed these models, we put them into practice, we've had them running, and now we're actually seeing a change overall in our population. So I think this is the last slide in this section, but really kind of like pulling it together. And, I focus more on kind of the data pieces, but really thinking about the deployment of AI in clinical settings. I talked a little bit about it on the previous slide, but again, we have a whole flow here. It's kind of analogous to what I showed with the knowledge discovery and databases process. Is there many steps, and it's very iterative and incremental. So, kind of a graphical view of what was on the previous slide is we need to identify recess and need. We don't want to build a model for something that's just to build a model. Ideally be based on a need, and in our kind of context of today's discussion is a clinical need. Again, a big part of it is study existing workflows. So we really want to study if it's something that we're implementing for a provider who may be interacting with a patient, really thinking about kind of risk of certain diagnoses or risk of some kind of complication. Think about what's the workflow right now and how would this fit into it, and not just throw a tool into a system and just seeing what happens. Defining the desired target state. So what's the outcome of that tool, acquire or develop. So we could, this is build or buy, depending on what is possible. An AI system, implement it in the target setting. Again, this is a whole area of work, and that can also be challenging, but there are success stories across the country. How do you put it in the target setting? Making sure it's working as appropriate. So these things change, knowledge changes. You might have developed your model and data from 2019, but we know it'll probably look different in 2020. And what does that mean for something that you've implemented? And so how do you think about updating your tool, which gets to the maintenance update? And sometimes tools just don't work and you have to de-implement them. And so there's a whole science behind this. Implementation science really tries to address all of these things. And again, I won't go into these, but this really talks about what are the challenges to advance and in the advancement and application of AI tools in clinical settings. And in addition to really the data parts that we talked more about, all these other things that need to be thought about when you actually want to put these things into practice. So that kind of ends kind of the challenges, opportunities. Hopefully it's been a helpful just overview of kind of all the things to think about that some of you may have already been doing pieces of or have done many of them, but just really an overview. And so what I thought I might try to do now is kind of talk about some of the work that we're doing within Rhode Island. Again, we haven't done all of it, but we've done pieces of it. But our vision is really to be able to do projects like that. So I thought maybe I'd start with just, the Brown Center for Biomedical Informatics. So I'm currently interim director as the founding associate director of that. Started it, I guess almost maybe 5 or 6 years ago now. And so really our goal is to advance biomedical discovery and healthcare delivery through informatics science, practice, and education. And so we have a pretty big, broad mission. Rhode Island is a small state. And so we really look to collaborate both within Brown as well as our healthcare affiliates, academic and healthcare organizations across Rhode Island, and now really going beyond. And we thought, with informatics, we're always about I's. So they're the 4 I's. We started with 3 I's: innovate, implement, inspire, and then added impact. And I think a lot of these just reflect really how we're tied with a lot of our mission is really tied with enabling AI-based healthcare. And so really innovating how data and technology are used. And so that's kind of, learning from the data, then implementing these digital innovations, so things we will learn from the data to improve biomedical discovery and healthcare delivery. Ideally, of course, wanting to impact health and healthcare through whatever data or technology-driven solution that we develop and implement and put into practice. And a big part of our center is really inspiration. So really the educational of really, we don't have enough people trained in this. And so really inspiring the next generation of researchers, providers, and consumers. So that's really our mission, which has been pretty much the same over the years. We've learned to kind of be a little more explicit about what we do, because I think some of you may know, kind of everyone seems to have a different view of what biomedical informatics is. So we've been trying to be good about saying, this is the scope of what we do. It is many different things, but we view it as we know a lot of different things and how to bring it together. And in this case, in the context of doing AI. So for our research, we have 4 faculty. We each have our own labs. I'll talk a little bit about my lab, which is the Clinical Informatics Innovation and Implementation Lab. But our other faculty have expertise in artificial intelligence and evaluation, global health, as well as precision and population medicine, and really kind of are in complementary areas. I think if you take us all together, we really represent expertise and experience in doing AI in healthcare. We have a number of educational programs that we've developed over the years, as well as courses that we all teach in. We work with high school students, undergraduate, graduate students, medical students, residents, fellows, postdocs, junior faculty, and then more senior faculty, and really a broad spectrum, really, again, to meet the mission of really want to train up the next generation. We do also have a service arm. So I think many institutions have CTSAs. We're part of a program called IDEA CTR. So Rhode Island is an IDEA state. And so we have a program called the IDEA CTR, program similar to CTSAs, really trying to build up infrastructure. And so that's what we've been working on doing. We have an initiative called the Unified Research Data Sharing and Analysis Initiative, really to address the barriers to getting data. So I think many of you know, sometimes it's hard to get data, particularly EHR data. And so what we've been working on for the last 5 years is how to enable use of EHR data or other health data for research purposes, and kind of working through many legal arrangements, technical arrangements. And so what we've done is work through that with some of our healthcare partners within the state and develop this secure environment at Brown, which we call URSA Stronghold. And it's essentially a secure data enclave where we can bring the data. We have a lot of software tools, so different programming languages to different database, different applications that we can then enable use of data in a secure environment. And so, as I mentioned, we take privacy and security very seriously. It's really kind of top of mind in everything we do, and be able to enable research in this secure environment. And there are many models like this elsewhere of doing it this way. And we also have high performance computing. But again, just to give you a sense of some of the resources we have and the activities of the center. And so we broadly tried advanced clinical and translational research, and really we have expertise and experience in the breadth of informatics subdisciplines, from bioinformatics to clinical informatics to population health informatics. As I mentioned, the learning health system is really trying to go from data to knowledge, which is more of what I'll talk for the remaining to talk about. But then learning from that, turning that knowledge into practice, and then studying the data coming from the practice to see, are we making a change? And really, this is a continuously learning health system. And so what I've tried to do here is kind of layer some of the techniques that are applicable for different parts. And so really for the data to knowledge, understanding data, techniques like information retrieval, standards and interoperability being critical to this step, but really the whole thing, natural language processing, machine learning, deep learning, and then visualization, all the things that I mentioned when we talked in the first part of the talk, of really kind of critical from going to data to knowledge. But again, on this side, all the different kind of skills and knowledge that you need to actually put things into practice. So I know I'm starting to run low on time. I'll try to get through this part quickly, but now kind of getting into the highlights. So a little more of what my lab does. So I'm calling it the CI3 lab. And so really focus on EHR. That's where most of my research has been for most of my career since I was in grad school. I've been working with electronic health record data. Back then, we mostly had homegrown systems. So at Columbia, we had a system called WebSys, where we're able to both use data from that system as well as build things into the system. So what I was able to do was build a mobile EHR to complement our web-based EHR. Things have changed a lot over time, I guess the last 20 years, where we're now seeing more vendor-based EHRs. And so my career has somehow evolved with that change from homegrown EHRs, where we really had a lot of access to the data as well as the technology, to working with vendor-based systems. And they also have evolved over the years, where there's much more ability to work with their technology and data. And so a lot of my earlier work was more in kind of system development, clinical decision support, and has kind of had some data mining, but I've then kind of in the middle part done a lot more data mining, natural language processing. And now I'm kind of trying to go back to balancing both of, we want to be able to look at our data as well as build these interventions or AI applications. And so this kind of shows some of the data set sources I work with, primarily EHR, and some of the methods. My early work was in data mining, but then started doing a lot with NLP standards, and these other different methods, and really trying to now bring them all together. Do have most of my projects kind of work broadly, but have started to specialize more in looking at things like determinants of health, which oftentimes aren't well documented in the EHR. So looking at both how to improve documentation as well as how to get the information out. A lot of it is still in free text. Things are getting better in our EHR systems where we now have kind of structured data collection, but a lot of that information is sometimes very subtle and in clinical notes. And so needing to both look carefully about how it's documented, as well as building natural language processing tools to pull it out, as well as using techniques to analyze those data. And so have done work early on in social, behavioral, and familial factors. And then also working with a number of collaborators in the mental health spaces, pediatric, and also the intersection. So working with clinicians in the suicidal thoughts and behaviors, looking at both how we identify and predict suicidal thoughts and behaviors. On the pediatric side, working on a number of projects in asthma, focused on technology development, but also looking at data to improve how we can identify kids with asthma. And then also at the intersection, have student working in autism. And also I have some active projects focused on pediatric behavioral health emergency services, and really looking at how those services are being used and what we could do to improve them. And so this graphic kind of shows, again, a lot of kind of what drives the work in my lab is, we collect data from EHRs, we study them, research, we hopefully will learn something new about prevention and treatment, and then be able to put them back into practice in some way through decision support. So again, we don't see the word AI here, but again, this is, pretty analogous to what I've shown earlier. Some of you may be familiar with the National COVID Cohort Collaborative, N3C, and so many of us across the country are working on trying to contribute our data into that to be able to study COVID-19. And so this is a visual from one of their slide decks. Again, very similar. We want the data, we want to learn knowledge, and eventually have decision support to better understand this condition. But what's really critical to this is terminologies and data models. And so that's why I felt it's important to kind of show this, is that's really fundamental, that for all of us to contribute our data, this was core to it. We had to be using the same data models as well as the same terminologies or language. EHR systems, I think we've talked a bit about, it's just kind of, longitudinal electronic record collects a lot of different information, really there to support patient care, decision support, quality management, outcomes reporting. What I'm going to talk about for the next few slides are something called the Health Information Exchange. And so we have a number of these across the country. Some states may have multiple. We have one Health Information Exchange in our state, and is one of our primary data sources for some of the work that we've been doing. And so basically it's a way to bring together EHR data, in our case, a state, from not just our hospitals, but from our primary care providers, from the health department, for specialty physicians, community care, all brought together into kind of essentially one database. And so we can really have the continuity of care. We have true longitudinal data for a patient, not just in one of these settings, but across all of them. And so that if someone comes to the hospital, they could potentially still get their information from when they went to see their PCP, even though if they're not in the healthcare system, and vice versa. And so within Rhode Island, the Rhode Island Quality Institute operates our state's health information exchange, which is called Current Care. And so this visual tries to, again, kind of show in a different way what I showed on the previous slide. We bring together data, particularly electronic health record data, as well as other data from very many different data sources. So you can imagine all these data sources. So there's over 500 essentially speaking different languages, and the HIE is responsible for basically integrating them so it looks like one statewide electronic health record. And so within our state, we use what's called an opt-in model. So you have to opt in to be part of our health information exchange. So not everyone goes in there. You have to just, enroll. And so we have over 500,000 patients, which reflects about over half of the population in our state, and then over 140 patient transactions. So these are just a couple examples. I know this is a very busy slide of how we're using data from our health information exchange, but in the last year, we've received funding as a center as a whole, and as part of kind of advanced CTR that I mentioned early on, of doing different work. And so using different AI techniques. And so we have funding from NSF to look at using information retrieval and graph mining techniques for symptom monitoring. we're engaging in this N3C effort to kind of contribute data that is going into a secure data enclave at NIH to be able to do different kinds of analyses, including machine learning analyses, and really a wonderful community effort. Locally, we also received funding for the RAD-Accept program, and so really studying testing and what are the barriers to testing, particularly in the Latinx population within Rhode Island. And so this is a nice study because it's mixed methods where we're doing qualitative analysis, talking with patients, talking with providers to see what are some of the barriers to testing, as well as complementing that with data analyses using data from our HIE. And then this one is another one where we're trying to say, can we build a learning health system in Rhode Island for COVID-19? And so this is a seed award we have where we're getting data, we're trying to standardize it. So we've standardized it to this, the OMOP model that I mentioned, and being able to do just a range of analyses, whether or not be clustering, supervised or unsupervised, so clustering or classification techniques, very similar to kind of, this is kind of our local complement to this national effort, and then being able to learn from the data and ideally put something into practice locally to really help with either diagnosis, treatment, and kind of longer term things. Thought I'd kind of highlight some of the other studies that some students have been working on. So this is actually a student, undergrad student who worked with me on an NLP project. We're using data from our current care health information exchange. So chief complaints, so those are oftentimes completely in free text. You know, patients come to the ED, they have a complaint, it's written in free text. And so there's been a lot of work over the years of trying to code those data, but this was our attempt to do it for our local data source. And so this graphic on the left tries to show some of our process of, again, there's lots of cleaning that needs to be done, you know, things like punctuation, abbreviations we found. And the goal here was basically to take these free texts and code it. And so here's an example. We might see nausea and vomiting, which we as humans can kind of recognize, but we want the computer to tell us, you know, what's the ICD-10 code for this? So in this study, we used an NLP system called MetaMap that was developed at the National Library of Medicine to basically take text and convert it to coded data. And so what this could do is say nausea and vomiting, okay, these are the UMLS concepts, but the UMLS, because it brings together many different terminologies or coding systems, can now tell me what the ICD-10 codes are. And within the EHR, usually there are these diagnosis codes will be in there. And so we do essentially have a reference standard. But to go from here to here required a lot of pre-processing, studying the data. Sometimes the codes themselves are even in the chief complaint. So trying to get those out, running MetaMap, and then doing the evaluation. And so here, initially, just because of granularity of ICD codes, the performance wasn't that great. But once we kind of did kind of higher level grouping, the performance is a little better. So again, just an example of, you know, the use of NLP in this case to take free text and turn it into structured data. Another example kind of in the mental health space, again, another natural language processing project. This time we used a data source called Mimic. It's an EHR, de-identified EHR data from Beth Israel Deaconess Medical Center. If you haven't come across this data set and if you're interested in looking at EHR data but don't have easy access, this is a great resource, particularly to do methods development. So if you're not able to get data readily where you are, you can use this data source that has a lot of EHR data. It's de-identified. They have a whole process to get access. And then you can kind of use it to kind of get familiar with what EHR data look like, do some analyses, while you may be able then to get more data locally to have more local relevance. But in this study, the goal of Ryan's study, who is a student in biostatistics, was to see if we can use text features to classify suicide attempts. So one of the challenges is suicide attempts, suicidal ideation are not well documented in diagnosis code. So oftentimes you need to go to text. And so things like discharge summaries is a source of text. And so what he did was focus on patients that were admitted for overdoses, got their discharge summaries, ran similarly the MetaMap tool. There are a number of other NLP tools for clinical text, but in this case, we use this one. It produces, as I showed on the previous slide, a bunch of UMLS CUIs. So turning it into a matrix like this. Here's kind of the example of here's structured data, family history data, and clinical notes. And essentially what MetaMap will do is go through this and then find the UMLS codes here. And so basically what he did is ran all these, ran map on all these discharge summaries, got all these codes, and then basically ran a number of statistical techniques to then see, can we, determine, is there something predictive of some combination of these features, these text features, in this case, UMLS concepts, that we could then use to determine if this patient, this note reflects a suicide attempt. And the performance here was pretty good. He used, of all, I think, UMLS concepts here, and then as well as a subset, and to see how it affected performance. But overall, again, a preliminary study, but kind of showed the potential of this approach, that the goal is hopefully with use of these kind of open source tools or readily available tools, this could then be a generalized approach that others could use. And again, this is an area that we're seeing a lot more activity in, use of NLP and machine learning for suicide prevention. And so really there's a lot of great examples out there space right now. Another study, again, a little bit different, but just to kind of show some of the work that's being done locally, is this one involved doing a comorbidity analysis for mental health in pediatric patients with autism using claims data. And so on the left, we kind of always like to use that same framework of, we select our data, we're focusing on autism in kids. And then these are some of the features we want to look at, doing some of the cleaning, transformation, a lot of times needing to group ICD codes because there's so many of them, and then doing different techniques. In this case, we used a technique called association rule mining that just shows, these comorbidities happen together often, and then sequential patterns. These comorbidities we may see happen often together sequentially. There's a number of techniques that can be used for that. And then to really assess this. And so this is a visualization. This was using R. There's a package called A Rules and A Rules Viz, and just showing, for these autism, focusing on their mental health comorbidities, these are the ones that we're seeing more often within this population. And so some of the things that kind of stood out as we're doing analyses was suicidal ideation. And so Katie is a PhD student right now. And so some of the thoughts that made her really interested in just basically looking at the results is thinking about safety planning, and that's really probably critical. And so she's now kind of expanding on that as part of her PhD work. So I'll try to wrap this up a little bit. Just a few more slides, but just wanted to also highlight, we've had other students work a lot in the machine learning space, particularly an MD PhD student and MD student. Back in 2017, we decided to adopt the Julia programming language. It was relatively new language in the data science community, but just because a lot of the features of it, we really decided that's the language we're going to pick, we're going to teach. And so all our courses, we teach Julia. But at the time, machine learning, there wasn't a lot in it. So it wasn't advanced like Python with having things like scikit-learn, and R having a lot of other statistical machine learning. So these students kind of spearhead this effort to develop this machine learning package, which they called PredictMD, and really addressed, because there was lack of a package at that time, and really targeted on clinicians and biomedical research, really to help them with AI research, including medical students. And they did an amazing job kind of building this out. It's very complex, but really to build kind of that pipeline where you have a data set and it can go from data set to evaluation to visualization. And so these days there are now machine learning packages out there in Julia. And so we're starting to think about, what's the next phase for PredictMD. But it still seems to kind of really touch upon all the needs, that really having a very simple way that you don't necessarily need to know how to program, just know enough to run it. And we've seen a lot of this everywhere, just having these pipelines and packages, but just wanted to kind of highlight this as another example of what we've been working on. And so, as I mentioned, they have nice documentation on the website, and, they have examples of going from pre-processing to dealing with things like class and balance to running all these different techniques. So logistic classification, random forest, support vector machine, and neural net. And the great thing, you can pick all of these, you get your data set in the right format, you kind of configure the code, it'll run any of these methods, it can run one of them, it can run all of them, and then it'll actually show you a comparison of them, calculating all the typical metrics, generating the ROC curves, so that you can quickly see what's going on and make adjustments. So I think this is almost my last slide, but just also want to highlight for those of you who may be interested in Julia, particularly development in Julia for health purposes. So Dylan, who's now still an MD PhD student with us, created the Julia Health Organization. So PredictMD is part of that. This is meant to complement work in kind of bioinformatics, computational biology, which they have BioJulia. And so these are just some of the other packages that others in our center, as well as Dylan, have been developing over the years, really to address different parts of kind of the needs in doing AI-driven studies. So with that, I'll end with this slide, but really I think our ultimate goal here is to develop this AI-enabled system for healthcare. And this is, I think, a nice graphic from a paper that came out last year. We've talked mostly here of developing machine learning models and establishing clinical utility and working towards developing systems, but there's a lot of other pieces around it. And really, I think what it nicely says in this paper really takes a transdisciplinary effort that, if we want to have these AI-enabled systems, we need methods from process improvement, design thinking, data science, IT implementation science. And I think also what's nice here, it kind of shows for each of these steps, really understanding what's going on, working with stakeholders, working with institutions, engaging leadership, getting buy-in, training, and then evaluating these systems really requires expertise from these areas, including data science and informatics. And with that, I'll end. I apologize for going a little over time. I don't know if there are questions, but I will stop here. And thank you for your attention. And hopefully some of this has been of help and of use.
Wow, what a fascinating talk. Thank you so much, Dr. Chen. I've been intrigued about all the work that you're doing over there at Brown. I will open the floor now to questions. I know there was one question that came in through the chat box. Please, if you have other questions that you would like to ask Dr. Chen, please add them to the chat box, or you can open your mic to talk. I don't know if you have seen the question in the chat box, otherwise I can read it out to you.
Yep, I see that question. Yeah, so Laboratory Department is exploring and evaluating the efficacy of transparency methods to support operators' ability to effectively judge the fitness of a specific model inference for a specific patient. So we do have another faculty member in our department who's starting to really specialize in explainable AI. I could either put you in touch or kind of ask him about some of the things that they're doing with explainable AI. But I think a lot of our work has kind of been early on. I think a lot of it has been kind of stuck in what I was saying, the early steps of just trying to get and clean data and running these methods. But I think that's kind of where we're kind of heading to next, and where I think most of these studies need to go next, is seeing how well they perform. We have training sets, we have test sets, but kind of, thinking about if we put into practice, how well it work with specific patients. So I think, I think some of us it's early on with us, but I am definitely happy to put you also in touch with some of our faculty who are really delving into kind of transparency and explainability.
Right. Before anyone else asks a question, I have one quick question that I wanted to bring up, if I may. All the packages that you have described, and I appreciate you giving an overview of packages that exist. One of the challenges that I've always faced with is how to deploy these packages within the data environments. Because of PHI, you have these data stored in warehouses that only accept installation of certain software. And some of these packages, they stand outside the firewall, and there's no way you can leverage them. How have you guys solved that issue, or how do you guys go about addressing that in order to leverage all the existing packages that are out there?
Yeah, so that is a big challenge. So kind of dealing with, oftentimes in healthcare systems, they use oftentimes Windows-based or proprietary, and are very concerned with installing open source tools. And then we oftentimes, I think, particularly kind of open science, will use open source tools. So some of the things that we've developed kind of in our service arm that I talked about is we developed basically a secure enclave at Brown. And so there was an environment called Stronghold, which is a secure computing environment. It's essentially cut off from the internet. And so it is hard to install packages, but we work closely with our information services to get packages needed. We've worked really hard over the years, and this is through our data sharing efforts, our URSA initiative, to work with health data partners to get data into the environment. And oftentimes, if you don't need PHI, you know, they may be comfortable sharing de-identified data, but even those, then they may want it to be housed in a secure environment. So that's what we've done. We've established an environment working with data partners to bring their data. We've set up a lot of technical pieces to be able to transfer data into this environment at the university. And then the university, you know, has a lot of these software tools in that environment that we can then work with. So that's one way that we've handled it. I know other places have looked a lot at cloud. And so that's, you know, cloud-based services. And again, some of them are HIPAA compliant. And so potentially using those, and that then you can install and get your packages there. But yeah, that is a big issue. Every institution, I think, has a different model because of the relationships. But if you have access to environment where you can have data and also install tools, and those are things, yeah, I'm happy to also talk, you know, offline with you about it. Just if there may be infrastructure there that you can leverage or kind of share our experiences, but it's a common challenge, yeah, of the data provider versus the tools that you need to use for analytics. And so, yeah, I still run into that too.
I appreciate that. Thank you. All right. Are there any other questions? Well, Dr. Chen's email was provided in the last slide, and you know, it's easy to find her contact information via Google. I think we can wrap up now if there are no other questions. I would like to take the opportunity on behalf of TDAI to thank you so much for giving us this excellent presentation. Unfortunately, our director, Tanya, had to leave early, and she sends her apologies for having to leave early, but we are all extremely grateful. This has been an excellent presentation, quite eye-opening to me, and I believe others have found this very useful. So thank you so much, and we look forward to staying in touch.
Great, thanks so much for the opportunity. Yeah, feel free to reach out and stay in touch. Thank you, everyone. Enjoy the rest of the day.
Thank you. Bye-bye.